I can use any extra point.
All right. Chatty group. I love your energy, but I need your attention. Okay, so let's continue where we left off. We barely started after the quiz, so there's not a lot of recap to go off of. We just started introducing resolution of two peaks, or resolution of peaks in general, and we talked a little bit about where do we start, and how we can choose multiple methods, and on what basis we choose our method. So we talked about that. Once you decide on the chromatographic separation, you also want to decide on your stationary and mobile phase. So even though you choose, okay, I'm going to go with reverse phase chromatography, you have to choose your stationary phase, because there is a C14, for example, column, C18, C30. So there is differences even within the columns of reverse phase chromatography. So you want to determine which one you want to use. So C30 will be the most hydrophobic, or most nonpolar or hydrophobic. C14 would be the least hydrophobic. So depending on the components you're trying to separate, you would go, which one would be better for my components? And then from there, you also have choice of mobile phase. You can choose, as an organic phase, you can choose acetonitrile, or you can choose methanol, for example. So again, you have a choice of which mobile phase to work with if you're building a gradient and increasing the strength of the mobile phase over time. So again, this relies on what the chemistry of your compounds that you're trying to separate. And then we choose the elution mode. That means, are we going to have isocratic? That means I don't change the concentration of my mobile phase for the entirety of the analysis time. So if my compounds separate nicely in a short period of time, I don't need to do anything. But if my compounds are so different in this mixture, one is going to interact for a long time on the column and another is going to interact short time on the column. In order to shorten my analysis time, I use gradient elution so that I can encourage that compound that interacting with the column for a long time to leave sooner. So then I would choose, but oftentimes when I'm developing a method, I would start with isocratic and see what happens. And then I work around and say, okay, isocratic is not going to work for me. I'm going to build a gradient to enhance my analysis efficiency and that. Two parameters that I would also look into and consider when developing my method is the flow rate and temperature. So with flow rate, that means how many milliliter of mobile phase I'm pumping per minute. Okay? So the speed of the movement of your mobile phase in your system. So this also needs to be adjusted and optimized. Again, you want a short analysis time. So with higher flow rate, compounds are going to come out sooner, but you don't want too high of a flow rate. They will come out too soon and not separate. Okay? So again, you want to choose your optimal flow rate with good separation and reasonable analysis time. Temperature also is important because with higher temperature, what happens to the viscosity of your mobile phase? Does it decrease or increase with higher temperature? The viscosity decreases. So with a decrease in viscosity, what would be the mobility? Mobility will be faster or slower, the movement? Faster. Great. So with a little bit of a higher temperature, your solutes are going to move faster down your column and reach equilibrium faster between the stationary phase and the mobile phase. With that, I have shorter analysis time, okay, and even sharper peaks. So you don't have a lot of diffusion in the column. You have movement in and out of the column into the mobile phase. So with high temperature, I get better resolution, sharper peaks, and shorter analysis time, but too high of a temperature is also not good. It's going to, again, let everything move fast and maybe lose the separation, co-elute. So again, here these are very important parameters for efficiency of the method, for better resolution, but we have to be careful in our choice, not to overdo it in temperature and flow rate. Okay, so I want to introduce some parameters that will help us understand resolution better. So a chromatogram is basically you will have chromatographic peaks that you want to integrate. And the chromatographic peaks, you want them to be separated so to get good quantification and good analysis data. So what we look at is retention time is the first thing that you would look at. So retention time is the time it takes for your first peak to come out, TR1. And then the second peak that you wanted to resolve from the first peak would take retention time TR2. Okay. Then one thing we want to correct for, or you could correct for, is the solvent front. For those that did the HPLC, I showed you that between two different HPLC units, you have different retention time. Why? Because the system is different, not identical. You have different tubing. There is different, since you have different length of tubing, there's different time that the compound's going to reach, or the solvent's going to reach the detector, or your compound's going to reach the detector. So the solvent front, the time it takes for the void volume to reach the detector is the time, or T0 we call it, or the time for the solvent front. So this is the solvent front, or we call it void volume, or the time for the void volume of the column to be seen. And I told you that the detector gives you the signal because from the time of injection to the time that the mobile phase reaches the detector is going to detect something. Oh, something just hit me. So it's going to give you a signal. And we call that the solvent front. From time of injection to the time that the solvent reaches the detector. So if from each system you have a different time that the solvent front is going to come out. So if we adjust for that, then the retention time can be more kind of calibrated. So the T prime is the adjusted retention time, taking into account the solvent front time. Okay, so that means it's the retention time minus the solvent front time. Other than the retention time, there is the retention volume. Is another, so you can measure the amount of volume it took for that compound to come out. But usually for our analysis purposes, we don't deal with the retention volume or the volume of the mobile phase it took for that sample to come out. We only look at retention time. And what we do usually, like we did in the HPLC lab, we look at the retention time of a standard to the retention time of our sample and try to say, okay, this is most likely the caffeine. But we need confirmation, obviously, but this is the first identification. If the retention times match the standard and your sample, then you kind of have like, okay, this could be the caffeine, could be the XYZ compound that we're looking at. So the alpha factor is an important factor. We call it separation factor. And it's basically the ratio of the retention time of peak 2 over peak 1. If the ratio is 1, that means they're not separated from each other. Right? If the retention time for peak 2 equals the retention time for peak 1, they're not separated. So the higher the alpha, the better separation you have. And that's what you want. You want a higher separation factor, obviously. This separation factor is impacted by the temperature and impacted obviously by the stationary phase and the mobile phase. So the selectivity of the stationary phase is very important. How selective is your stationary phase? It will allow separation of the compounds based on the selectivity of your stationary phase. Mobile phase, also those of you that took the HPLC, there was a question on whether you use acetonitrile and methanol. What happens if you use acetonitrile and what happens if you use methanol? If you use methanol, methanol is more polar than acetonitrile. Okay, so it's not as strong of an organic solvent as acetonitrile is. So if you use methanol, it might take longer for the compounds to elute, but you might get better separation if you have compounds that are very similar in their characteristics or affinity to your stationary phase. If you have two compounds that are very similar in their association to the stationary phase and you use acetonitrile, they will come out together. If I use a less polar organic acid, they will phase, they will separate better. Okay, so they won't come out together. They won't jump out together if you use a highly strong organic mobile phase. So the separation factors, that is impacted by the type of stationary phase, the mobile phase, and again by temperature. With higher temperature, we have higher movement. Your peaks will be sharper, not broad. And the sharper the peak, the better the separation. If they're broad, they kind of overlap each other. Okay, so I'm going to use the concept of resolution in mathematical manner and different factors impacting resolution. So resolution, by definition, in simple terms, that means separation of two peaks or resolving of two peaks or two compounds from each other. Important in determining resolution is retention time. And then another important factor is the width of your chromatographic peak. So the narrower the width, that means the sharper the peak, the better your chances of getting resolution. The broader the peak, the lower the chances of getting resolution. So let me just clarify this a little bit here. So if you have two peaks, they have very close retention time, but they are sharp and really nicely separated because they are sharp peaks. That means they reached equilibrium faster, they moved faster, and they were able to separate and leave the column in a reasonably fast manner. So there was sharp peak. However, if for some reason my compounds are diffusing in the column and staying longer with the column, okay, that's new. All right. So if I have compounds that are sticking longer on the column and they're not equilibrating fast, my peak will be wide. So at the same retention time, I'm just going to get this peak. Okay? So what happened there? These two peaks did not separate. They came up as one. Or I will have this kind of shape. Right there. So they might have separated slightly. So you know that they are there, same retention time, but they kind of overlapped. So the narrower the width, the better the resolution is going to be. So it's inversely proportional to the width of your peak. Okay? And it's directly proportional to the difference in time. The difference in time is the difference between retention time 1 and retention time 2. So the bigger the difference, the higher is the resolution. Okay. That is a simple way of looking at it. But if I want to look at resolution in terms of the different factors that impact resolution, there are 3 different factors that impact resolution. So these factors, we're going to talk about each one of them separately, but I have the first factor, which is the efficiency of the column. The efficiency of the column is related to the number of theoretical plates. Who heard of this term before? So you've heard about it somewhere in life. Why only 2 people heard about it? Where? Where did you hear about it?
In organic chemistry.
Okay, then all of you should have heard about it. But forgotten about it is a different story. Right? You've heard about it. We will remember it here. So number of theoretical plates is directly related, is the indication of efficiency. The separation factor is an indication of selectivity. And the capacity is indicated by the K prime, which is the retention time in comparison to the solvent front. Okay, and we'll talk about it later. So we have efficiency, selectivity, capacity. All these terms impact resolution. Okay, now we'll save the recap questions for later and move on to here. Describing the number of theoretical plates can be complex, but I'd like to simplify it as much as I can to remind you what it is. Okay. So each column is obviously made up of your stationary phase, and it has different dimensions. So some columns are long columns, some are shorter columns. Okay. But if we just say, okay, here's my column, and I'm trying to separate a particular component X, so mu, and I want to see the efficiency of the column that leads to a chromatogram with a very nice sharp peak as such. I don't want a peak that looks like this. I don't want that. Okay. So now, what would make this peak come out sharp like this and in a short period of time? So we want to imagine that the column is divided into segments. And each segment is called a theoretical plate. So this segment is where equilibrium happens. Of X. The equilibrium is between the stationary phase and the mobile phase. The quicker X reaches equilibrium, that means this distance is short. The shorter the distance, I have less diffusion. Because when you inject, you're injecting your sample on top of this column here. When you inject it, it's going to be a thin line on top of the column, but once it goes through the stationary phase, there is diffusion, and then there is in and out into the mobile phase. On the stationary phase, in the mobile phase, going in and out and reaching equilibrium. If it stays sharp here and sharp here and sharp here as it moves down, it will be a sharp peak. If it starts diffusing, that means I have my theoretical plate is longer. So the time to reach equilibrium is longer. That means my compound is diffusing more on the column rather than going in and out and moving with the mobile phase, in and out and moving with the mobile phase. When it diffuses, then this leads to that. This leads to, okay, it's coming out and it's taking time to come out. It's diffusing. So every point here is in relation to time. So if it took longer distance, if it occupies longer distance on your stationary phase, that means it's going to come out over a long period of time. And that's what makes it, this is the signal. That's the signal that you detect at each time point. So you're getting this sample coming out over a long period of time. That's why your peak is broad. However, if it remains sharp with shorter distance for equilibrium, then it will come out sharp and most likely be separated from the next compound nicely without having a broad peak overlapping another peak. Are we all following? So we don't want diffusion. We want equilibrium to be reached quicker between stationary phase and mobile phase. The compound remains sharp as it goes down and results in a sharp peak, better resolution. Okay? So the length of, or the height of the theoretical plate is important. The longer length, the lower is the resolution. The shorter length is the shorter, the better is the resolution. So over time, the column loses efficiency. What happened is the same compound that you run this month versus running it in a year on the same column, it will potentially reach equilibrium slower. Why is that? Because functional groups are lost over time. They are blocked over time or stripped off over time. Okay? Or you have more pores because you lose particles from your stationary phase or dissolve into your mobile phase. Then you have empty spaces in your column, void. Then your compound of interest is going in and kind of being lost inside of the column. So it takes longer for it to reach equilibrium. So over time, my number of theoretical plates go down. Okay? So I kind of lose efficiency over time. So the higher number of theoretical plates, the higher is the resolution, obviously. Now, one thing is I want to point out is that number of theoretical plates is different between different solutes. So the same column, but different solutes might have different number of theoretical plates because it depends on how they're interacting with the stationary phase. So the number of theoretical plates is very characteristic to the type of solute you are trying to separate, and it is also proportional to the length of the column. Okay? The longer the column, the more theoretical plates you're going to have, the better is the resolution. Okay? So that's why longer, thinner columns, you get more efficiency and better separation of the peaks than shorter, bulkier, thicker columns. Okay. So, because there is a difference in column length, we want to look at take into account the length of the column by just looking at the height equivalent of the theoretical plate. So we don't want to include in our equation the length of the column. We just want to look at the height of each one of those. So how do I get that? And we call it height equivalent of a theoretical plate. Okay? So it's the length of the column by the number of theoretical plates. So the more theoretical plates I have, the shorter is the height of the equivalent of theoretical plate. So the shorter the height equivalent of theoretical plate, the better is my resolution. So here the efficiency factor is, in this case, of the height equivalent of theoretical plate, is related to these three factors. Okay, so the first one, A, is Eddy's diffusion. Okay, you can write that down. B is longitudinal diffusion, and C is mass transfer. And I'm going to talk about each one of them separately. So I'll start with eddies diffusion. Okay. So what's in the column? In the column is your stationary phase. And what is the stationary phase? Stationary phase made up of very small particles. Some of these particles can be porous. So if you have a column and another one has packing material that is potentially large versus one that has really small, well-packed particle size. Okay, so I want to think about, say this is your stream of the mobile phase coming in. So think about this is a river and this is water and these are rocks. Okay? So if you have large rocks versus small rocks, which type will cause deviation more in the stream of water? The bigger rocks. So when the water hits bigger rocks, it's going to go in many different directions. It's going to have many different directions, and the diffusion would be higher. Okay? So your compound is going to diffuse because it's going to go into many different directions. Whereas when you have small particles packed really well with very minimal space between them, you're going to go in and you don't have a change in direction as much. You don't go all the way, and you're going to stay mostly as a thin and non-diffused low diffusion. Okay, so then you'll have better equilibrium, reaching equilibrium faster. So in this case, I will have shorter height equivalent of a theoretical plane. My A value, eddy diffusion, will be lower. Okay, I have less of diffusion here than I would have there. Okay, so the second one, longitudinal diffusion. Longitudinal diffusion has to do with the fact that in any case, your compound is going to move from point A to point B by diffusion. Okay? So the more it diffuses downwards versus going in and out and going this direction, then you would have a higher longitudinal diffusion. You can see here that this factor is impacted by flow rate. The mu here is a flow rate. The slower the flow rate, the more you have longitudinal diffusion. That's why you don't want too slow of a flow rate. That's why slow flow rate causes broadening of the peak. The higher the flow rate, because it's inversely proportional, the higher the flow rate, the more the lower this whole longitudinal diffusion is going to be. The shorter is your height equivalent of the theoretical. So flow rate plays a big role in the diffusion downwards and going in and out. The last factor is the mass transfer. So that means how fast your molecule or compound is going between the stationary phase and the mobile phase. If you have particles that have pores or large pores, when your solute is moving in and out, if it enters a pore here, it's going to be delayed. So the more porous it is, or whenever you lose functional groups, you will have more pores because you lost functional groups over time when you are using the column over and over and over. Then you will have more pores, then you will have lower or shorter longer transfer time. So the transfer time will be longer. But if you have well-packed material, very small pore size, then you would have fast transfer in and out. So if you have a fast transfer, you will have a better or a lower height equivalent of theoretical plane. Again, this is influenced by the flow rate. With higher flow rate, you have higher movement, reaching equilibrium faster, but too high of a flow rate will not let you get to equilibrium. Okay? Will not allow for equilibrium, and this will lead to coelution. Okay? That's why flow rate is in both ways. Too slow is not good, too high is not good either. Too high is also going to impact your height equivalent of theoretical plate. You won't get equilibrium. You won't reach an equilibrium. So if we look here, so the height equivalent of theoretical plane in relation to the flow rate. So you have to have a certain flow rate that gives you the lowest height equivalent theoretical plane. Below that, it would be too slow, and we increase the B factor here. Above that, it will be too fast, and you increase the C factor here. In both cases, this will lead to higher, longer height equivalent of theoretical plate. Okay, so this is the impact of a flow rate. Again, we talked about briefly the impact of temperature. When you have high temperature, it helps the movement, it helps with reducing the B factor and enhancing the movement and getting to better mass transfer. But if it's too high of a temperature, then everything moves fast and you don't get separation. So that's why too high each case is not good, and too low each case is not good. So you want to find the optimum for the type of compounds that you are separating. Any topic you'd like me to repeat, any concept. This is all also very well described in the book chapter, and obviously everything is recorded, so you can go back and listen to that or read the book chapter. Selectivity is the second factor that impacts resolution, and basically this has to do with the nature of your stationary phase. So the more selective your stationary phase is, the more separation you're going to get between two compounds. And the same with the mobile phase. The same example I said earlier about using acetonitrile versus methanol, for example. So the selectivity is impacted by the choice of your stationary phase and the choice of the mobile phase. And it's more important than the efficiency of the column. If you lose selectivity of the column, then this is worse than losing efficiency of the column. And one way you can use selectivity of the column if some of your functional groups are stripped off with excess use. So if we look at the resolution equation here, you can see that it is directly related to the selectivity and quadratically related to the number of theoretical planes. So it is a more important factor. Last is the capacity. That means it has to do with, this is the capacity factor, so it has to do with the retention time in comparison to the solvent front. So when you lose capacity, so you have lost some functional groups that stay on the column, so you have less capacity for your solutes to interact with the column, then they will come sooner. They will elute sooner. So if they're eluting sooner, then this factor is going to be low, because the difference between the retention time and the solvent front will be lower. So if I have this compound here eluting at, let's say, 7 minutes, if I lose capacity of the column by stripping off some of my functional groups, the retention time might go to 5 minutes. So at 5 minutes, I'll be getting closer to another component component that already did not interact a lot with the column and eluting, let's say, at 4 minutes. So when this elutes at 5 and this is eluting at 4, then I'm losing separation. So I lose resolution. Okay, any questions about resolution? This is your time to ask. I'm happy to repeat anything. You're all expert in resolution. If I do a pop quiz now, you'll all get 100%. Hayden goes out. Cindy. It could potentially, but if we say B already does not interact a lot with the column. Let's say you have a non-polar column and a polar mobile phase. B is already polar and it's not going to interact anyway. So it will just elute sooner anyway. But this one that was interacting with the column would go more sooner than B would. Yeah. Okay. Pop quiz. Okay, Sophie's saving you guys by asking a question.
So on the separation resolution HETP equation, so term C.
Capacity. No,
there's resistance to mass transfer.
Oh, this is capacity. Term C in efficiency.
Yeah.
Yes.
So you can
Resistance to mass transfer. The more you have resistance, then the higher is your high equivalent theoretical plate, and the lower is your resolution.
Okay, so the high equivalent theoretical plate is low resolution.
Exactly.
Okay.
Because that means, remember how I drew them, so it takes longer to reach equilibrium. Then your compound is diffusing within the column rather than equilibrating in and out. You want it to equilibrate in and out of your stationary phase. If it doesn't, it's moving by diffusion downward. That means it's spreading. And when it's spreading, that means your peak is broad. Okay. All right, no pop quiz. I was just teasing. All right, so in chromatography, you have two types of analysis. You can do qualitative or quantitative. So in qualitative, that means you only want to know what you have in there. So either you want to see if a certain compound is there or not, or you want to identify certain components, determine what they are. So that's what's qualitative, is you're not really you're not going after concentration in this case. So in order to identify, the first thing you would do is looking at retention time of the peak of interest, of the solute of interest, and what you think is the standard for that peak. So if the retention time is similar, that's your first mode of identification. Another way to identify is, we call it spike sample. That means if you want to know for sure if this is your glucose peak, just for simplicity, I would add glucose to my sample and inject and monitor which peak is going to increase in height. So I spike my sample. The photodiode array detector, which I'll talk about more in detail when I start spectroscopy, but those of you that took HPLC, this is the detector that gives me a spectra or a scan, absorption over a range of wavelength. So this kind of like fingerprint of your compound, every compound supposedly absorbs light differently. So each compound will have a different absorption at different wavelengths. So that means the spectra, in this case, you have the signal or the absorption here. And here you have a range, let's say 200 nanometer, let's say to 400 nanometer, just your UV range. Then you would have a unique spectrum spectra that gives you an absorption at the range of wavelength. Like here it doesn't absorb, no absorption, and here we have an absorption. And this is lambda max. That means the wavelength, let's say this is 280 for proteins, the wavelength at which you have maximum absorption. So this spectra gives me another form of identification. Other than retention time, I can compare the absorption pattern and determine whether or not this is the compound of interest. Sometimes I look at absorption using multiple detectors. I can do fluorescence, I can do absorption, and then look how these compounds are different. Some compounds do not fluoresce the same way. They might absorb this at the same wavelength, but one might fluoresce, another might not fluoresce. So that could help me identify. Another is taking peak ratio. That means absorption, let's say, at 214 versus absorption at 280. I take the ratio of the absorption. Every compound will have a different absorption ratio at two different wavelengths. So I can, again, use that to enhance the power of detection. If I don't get separation, I use a different chromatography mode. Sometimes I do, let's say, size exclusion and follow that by reverse phase, or size exclusion and followed by ion exchange. Two modes of separation, because some compounds might have the same molecular weight but differ in polarity. So I might not be able to separate them based on the molecular weight. Then I would have to separate them based on another chemical. Another powerful tool is mass spectrometry, which you'll learn about next week and in lab the week after. So here you look at not only retention time and standards, you can also get molecular weight and fragments. When you fragment your sample, depending on the ionization source, you can start having identification patterns. What this compound is made up of, and also what's the molecular weight, which is another powerful tool of identification. So the last piece I want to talk about is quantitative analysis. So in quantitative analysis, that means I definitely want to get the good separation so I can get an individual peak. And there I can either take peak height or peak area. Mostly we go with peak area. Why? Because peak height can fluctuate based on the conditions of separation and the status of the column. So sometimes your peak is sharp, but something might cause it to be a little wide. But the area will not potentially change. The height of the peak might change over time, but the area will not change over time. So potentially, I don't want to use height. Mostly I use peak area for concentration determination. Of course, in the past, you would use simple methods to get the peak area, using strip chart recorder, for example. But nowadays, we have data analysis software that would calculate the area under the peak for you. Makes it easier. So here's where a lot of students get confused. What's the difference between external standard and internal standard? For quantification, you need at least the external standard. You cannot quantitate without external standards. You cannot quantitate with an internal standard alone.
I'll have to
Yeah.
I think we use external standard during the HPLC.
Yes. Yes. For HPLC, we use external standard. Okay? So that means with external, you're preparing the standards that are in your sample. So if you have caffeine, you get a caffeine standard and you prepare it outside of the sample, different concentrations. So you would plot different concentrations, like some of you already did the HPLC, and then you plot the area, and you get the regression equation, the equation of the line, where it will give you the relationship between y and x, So when you have an area for your unknown, you can plug it in your equation and you can calculate the concentration, which is X. Pretty simple. In order to get concentration in your unknown, you need to plot external standard. Now, what is internal standard? Does anybody know? Yes, Sam? Inside of my sample and with my external standard as well. The same concentration I would put in all of my samples and in all of my external standards. It's there everywhere at the same concentration. Okay? Why would I need an internal standard? What does it help me with? Adele?
It's like a reference.
It's a reference, and not just a reference, it has a very important job. Anybody can guess? Huh?
You know the product loss is on.
Loss. The loss. That he said a very key word. In sample preparation, sometimes you have so many different steps, you might lose some of your components along the way. If you put an internal standard in there that is similar to your compound, but it's not your compound, but similar to it, it will, in your sample at the beginning of the preparation, it will go through the entire sample prep. So any loss in your solute or in your component of interest will be lost in your internal standard as well. So you are correcting for sample preparation error or injection error. If you're injecting onto your GC or onto your HPLC and there is an injection error, especially manual injection, that will also be, the error will also be applied to the internal standard. Then when you correct for that, then your values will be more precise and more accurate. Okay. So the internal standard goes in all of your standards and in all of your samples. It should not co-elute with any of your components. So look at this example here. So let's say molasses. In molasses you have glucose, fructose, sucrose. You don't have lactose. Lactose is sugar. And it elutes within the retention time, within the analysis time. You want it to come out within your analysis time. You don't want to change your analysis time. But you don't want it to come out with anything else. So here's your internal standard. It doesn't come out with anything else. Okay? So for example, for GC, for fatty acid analysis, you know that you don't have C4, maybe, or you don't have, I don't know, C14, I don't know. You pick a fatty acid that is not present in your sample as your internal standard. So it does not come out. It is similar in composition and it's not present naturally in your sample. So three things: not present naturally in your sample, related in the chemistry and structure to your samples, and does not co-elute with your constituents that you're analyzing. So three things. If I ask you in a quiz, what are the characteristics? These are the three characteristics. Okay, now lastly, before I let you go, I have 1 minute. Lastly, when you plot your calibration curve, to take into account the internal standard that is present in all your samples and all of your standards, this is how you plot it. You plot the concentration of your external standard. See, external standard is important, needs to be there. No quantification without external standard. So you put your external standard concentration here. On the y-axis, instead of just the absorption of your compound, the absorption of your compound relative to the absorption of the internal standard. So you're correcting for the internal standard in everything, whether it's the standard or your sample. So you get the absorption divided by the absorption of your internal standard, and you plot that for X, Y, Z. That means those are the different components that you are measuring in your sample. So you would have an equation of the line for each standard. And then, for each compound of interest, you get the absorption divided by the absorption of the internal standard. Then use that in your equation of the line as the y. and then you calculate the concentration of that particular compound. So these three here, that's just to tell you that there might be three components that you're trying to quantitate in your sample. Okay? You might be quantitating only 1, or 2, or 3, or 100, but in any case, your internal standard will be used to correct that. Okay, so next week we'll continue with HPLC GC labs. We're just going to swap the groups. Have a great weekend.